In this video, we'll see how simple linear regression might not work and multiple linear regression actually might be better. So let's go back to our regression of final exam score on missed classes. So we were saying that we can explain the final exam score based on missed lectures and perhaps some other variables, right? So let's see what happens if we only estimate this regression with one explanatory variable. So here you're going to see that the final exam score is out of 40 points and the missed lectures are out of 32 lectures. And then we will introduce prior GPA as another explanatory variable or a control. So let's see what we find. So if we regress this variable final on missed lectures, we find that the coefficient is actually negative, which basically means that as missed lectures increase, the final exam score drops, okay? Which is fine, right? We can basically say, we can interpret this as the following. We can say 10 more missed classes reduces the predicted score by about 1.2 points. Okay, and this is out of 40, remember. But when we introduce prior GPA, then we find that this coefficient is actually positive. So maybe we were not capturing, even though this seems intuitive, that if you miss more lectures, that your final exam score might drop. This may not be something that should explain all the variation in the final score. Okay, so maybe there are some other things, and that's what we're trying to capture with the preparedness or the prior GPA. So here, notice that the sign on this missed lecture changes from negative to positive, and the coefficient itself, right? I mean, even though it changes the sign, that the value also changes. So this is what we're seeing here. So the coefficient on missed actually becomes positive, but it is very small, right? It's actually we'll see in our empirical exercise that it is actually not going to be statistically significant or different from zero. Even if it is significant, it will not be statistically different than zero. And the coefficient on prior GPA, because we got this coefficient to be 3.24, is basically saying that if there was a 1 point increase in prior GPA, which an example would be if your GPA went from 2.5 to 3.5 or 3.5 to 4.5, that predicts a final exam score that is 3.24 points higher on a scale of 40, right? And so you might be wondering, well, why did this happen, right? Why is this coefficient why is this estimate now turned positive? If you try to look at the correlation between these two variables, what is the correlation between prior GPA and missed lectures? That correlation is actually negative, right? Which means that on average, students with higher previous GPAs miss fewer lectures, right? So if your prior GPA is high, right? If there's an increase in this, there is a decrease in missed lectures. Okay, so basically there was this relationship that was not captured when we were running the simple linear regression. Okay, and we can notice this with other types of regressions as well. So if we wanted to estimate returns to education, we could run that regression that we were interested in previous lectures as well, just the regressing log wage on education. And here we see that there's a 9.9% return on education, right? But if we introduced IQ, if you want to capture some sort of intelligence or some sort of ability in some way. It's an imperfect measure, or not a measure at all. But, let's say we had this data and we ran this, then, notice that as you start controlling for more variables, the return to education, the coefficient here decreased, right? So it became 7.3%. Okay. And you might want to look at what is the correlation between education and IQ. So in that data set, this may or may not be true in other data sets, but at least in that data set, it was positive. Okay. So again, multiple linear regression is trying to partial out or isolate the effect of that independent variable, right? It's partialing out the effect of other variables and trying to isolate the effect that one variable has on y. Okay. And this is what we mean when we say we are holding other factors fixed. Okay. So the nice thing, like I said before, of multiple linear regression is that it gives us the ceteris paribus interpretation. And we don't really have to go out and find two people with the same prior GPAs. We can run a regression. If we have enough variation in our data, we can just run a regression of y on a bunch of x's and we can try to capture the effects. Or we can find, or we don't need to have two people with the same IQ in our data set. We can basically control for IQ, and the way we will interpret beta 1 when we estimate is that is the return to education, holding everything else, at least here in our regression, this is IQ. So holding IQ constant for all the variables, all the cross-sectional units in our sample. So there are some properties that are always going to hold. For example, we said that even in the simple linear regression model, the residuals always average to 0. So we can always test for this. And this implies that the mean of your dependent variable is equal to the mean of your predicted variable or your predicted y. Okay. And also, that explanatory variables are uncorrelated with the residuals in the sample, okay? And so this is, this is something that we want to keep in mind. And always remember that the sample averages always fall on that OLS regression line, that line of best fit in your data. So notice that here, if we were to plug in the means of these x's and we calculate what this right hand side is, this is always going to equal y bar. Okay, and similarly our r square is pretty much the same as before. Here we're saying that the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. So you come up with such an expression for r squared that we discussed in the simple linear regression case. Okay, and one last thing to keep in mind is that the r square lies between 0 and 1. Okay, and if you add more independent variables, typically the r square is going to go up a little. Okay, so we don't want to get so fixated on r square. So don't get fixated, or don't get too fixated on r square. Okay, typically our sum of squared residuals will fall when we introduce a new variable x. Okay, and as long as, typically another x cannot make the sum of squared residuals increase. Okay. So you want to keep that in mind.